Okay, guys, in this lecture, we're going to learn about the potential and the electric field of a dipole. This last section of chapter 3, I think, is the last thing we're going to do this quarter. So let's finish strong. And I think this is a really cool thing we're about to learn about. I'll give you guys some examples why in the next lecture. But first, we just got to go back to the old dipole. This is something you guys did learn about in 183, but now we're going to revisit it at a more advanced level. Okay, so let's just remember what a dipole is to begin with. All right, so this is an electric dipole. Okay, we think about dipoles as being 2 point charges, in particular a positive and a negative one, separated by some distance, okay? And in this case, we'll define that distance with a vector pointing up from the negative to the positive, and we'll call that vector D, okay? So a dipole in this case, okay, is 2. They're equal in magnitude. But opposite in sign. Charges. Okay. And they're separated by some distance, d. Okay. This particular dipole has a dipole moment that is defined by P. So P is what we use for dipole moment. Dipole moment is a vector. Okay. It's in the same direction as the vector D, but it's scaled by the charge of an individual one of the particles, just the magnitude. So this is the magnitude of one charge. Right, and then this is the separation distance, which we've defined here in the picture, okay? So if I wanted to calculate the potential of this dipole, I could do that. I'm just going to steal this image here, paste it down here, and I'm going to give myself a coordinate system that I'm going to use to actually calculate the potential. The easiest way to do it is to put the origin right halfway in between them, okay, such that this distance here from, say, the positive charge to the origin would be d over 2. I'll call this my z-axis. Doesn't really matter what the other axis is, okay, and I want to evaluate the potential at some point p up here, okay, just like we normally would, and of course p has coordinates of x, y, and z in my coordinate system. Okay, so if I wanted to figure out the potential, I'm going to do it the normal way, okay? So if you guys remember, the potential of a point charge is Q over 4 pi epsilon naught divided by the separation vector, okay? So I just need to define some vectors on this graphic here. I'm going to define the position vector for my Q1. Okay, that's going to look like R. I'll call that R minus prime. Let me zoom in on this guy so I can do it a little better. Okay, I also need a position vector for my positive charge. Okay, again, if you guys were to do this, you might want to just get rid of that D vector just to make it a little bit cleaner. But I'm going to call that R plus prime. Okay. And then I need to define the separation vectors, which are going to point from the source, which is the charge here, okay, to the point where I'm trying to evaluate the potential. So this would be my separation vector for the negative charge. And here, that would be my separation vector for the positive charge, okay? So with all that defined, I can now write an equation that will give me the potential at point P. At P, that's going to be equal to Q over 4 pi epsilon naught, or just pulled the Q out of each. Okay, and then it's going to be 1 over the magnitude of our positive separation vector minus, and the minus sign comes from the fact that this charge is negative, and I pulled the charge out here, minus the magnitude of that negative separation vector. Okay, we can go ahead and quickly just evaluate both of those vectors together. So this plus minus here, basically just follow it through. It's just allowing us to evaluate what the positive separation vector is and what the negative separation vector is at the same time. So this basically means plus or minus, okay? So you're going to see a bunch of pluses or minuses. Either way, okay, we're going to take the position vector of our point. Okay, so I didn't actually draw that on the picture, but I can. That would look like that guy. Minus our position vectors for our charges. Okay, so that would be plus and minus. That's going to be equal to, again, if I just remember what each of these R's are, this R is just X, Y, Z. These R's are the X, Y, Z's of these 2 points. That's going to give me X squared plus Y squared, right? Because these guys have an X equals 0. Sorry, a Y equals 0 and a Z equals 0, both of them. Okay, and then the last one, because they're along the Z axis, that's not going to be 0. So the top one is going to be positive. So I'm going to get Z minus D over 2 for the top charge here, because this one's at, let me just write the coordinates for these guys. This one's at a coordinate of 0, 0, D over 2. And then down here, this one's at 0, 0, negative D over 2. Okay, so that's going to give me, it's going to flip the sign here because I'm subtracting this position vector from this one. I need a square there. Okay, so those are the position vectors of each of the charges. I can rewrite what's under that square root. I'm just going to gather some terms here. Okay, so I'm basically going to actually multiply that out. Okay, and when I do that, I'll get X squared plus Y squared plus Z squared. And then what I'm going to be left with is negative plus 2 times D over 2 times Z, okay, plus D squared over 4, and all of that is going to be to the 1/2. All right, so I'm going to look at that one more time here. The reason why I did that is I can take all of this stuff here. That's just going to be R squared again. And then if I simplify what I'm left with, I've got plus D squared over 4, and then minus plus, the 2's are going to cancel here. So I just get dz to the 1/2, okay? All right, so this, by the way, this guy, this is what was just under here. So we haven't really figured out the potential yet. So now we need to go back and actually do that. Okay, so now we're going to approximate what that's going to look like by saying that we're going to get really, really far away. Okay, so if we get far away, so P moves far from the charges, or you could think of that like R being much, much greater than D, the separation vector, R being the distance from the origin to the point charge, okay? Or you can think as we get far away, the actual separation of those two charges is going to go to 0. Those are just different ways, but basically we're trying to get really far away. The charges are going to look like they're close together, okay? In that limit, so we're going to take a limit as d goes to 0. We're going to take a limit of this guy, which was what we figured out for our separation vectors. We're going to say this is getting small because it's a small term squared. D is small, so d squared is extra small. Okay, so we're going to say that this is approximately equal to, I'm going to pull the r out, 1 minus plus dz over r squared. That's what I get when I pull the r out, plus some extra terms, which are our higher order terms that we are going to neglect for now. Okay, and now I can further simplify this by using the binomial expansion. And again, this is a common technique that we've used throughout this course and really is used throughout physics to take something complicated like this and simplify it, because oftentimes these higher order terms, right, get really, really small really fast. So they're actually not that significant. It's just the leading terms that matter. Okay, so if you remember, what we do when we take the binomial expansion is we can pull down this exponent here, multiply it by this guy, and then get rid of the rest of the terms. Now the separation vector is going to be equal to r times 1 minus plus 1/2 dz over r squared. Okay, so we're going to approximate the separation vector as that. That's nice because we got rid of that square root. Okay, but we're really looking for the inverse. Because again, we're looking for the potential ultimately, which has 1 over the separation vector in it. Okay, so really that is going to be equal to 1 over r times all this stuff. Okay, we're going to use that binomial expansion again. Just kind of amazing. You can just keep applying it over and over again. But again, d is still small, so we can still do that. Okay, and when we do that, this simplifies again, and we get 1 over r, 1. That's going to flip the sign here because we're going to get a -1 moving out front here, so that's why this is flipped. Okay, and you still have the 1/2 dz over r squared. And now I'm going to go ahead and say, again, there's some higher order terms that we're going to neglect that's in the dot, dot, dot. Okay, so we can now, we're going to approximate v as, we're going to take what we started with, which was that v was equal to 1 over 4 pi epsilon naught, sorry, q over 4 pi epsilon naught times 1 over the magnitude of our positive separation vector minus 1 over the magnitude of our negative separation vector. But now we've approximated what those are. Okay, so if I write in our expansion for those terms instead, okay, so we use the binomial expansion, assuming we're far away from the charges to come up with these expressions. We're going to grab, if I look here, we need to grab the positive sign for the positive separation vector, the negative for the negative separation vector. So this one's going to come out positive. Again, we're going to have some higher order terms, which we are going to ultimately neglect. And we get 1 over r, 1 minus 1/2 dz over r squared plus some higher order terms. Okay, again, these are higher order stuff that we don't actually want to keep track. Okay, if I look at these two terms and kind of see what's going to happen when we do that subtraction, the first term here is going to cancel because that's a positive. We're subtracting it on the other side. But here we've got two negative signs, so those terms are actually going to add together. And that's going to give our approximate potential to be Q over 4 pi epsilon naught over dz r to the third, okay, when we distribute out this 1 over r over here. And then we've got two halves we're going to add together. Okay, I can rearrange this a little bit, and I'm going to say that's 1 over 4 pi epsilon naught. I'm going to group together the q and the d, and I'm going to keep the z by itself there. Okay, if I remember, r is equal to x, y, and z. So the z component of the r vector is just equal to z, okay? So that means that I can let, in this particular case, the way that I have my axes set up, I can let the dipole moment, which is p times q times that vector d, I can rewrite that as q times the magnitude of the vector d times z hat. Okay, and I can do that again because of the way that I drew this particular picture. So I'm going to copy this over. You guys remember the way I put my coordinate system? The d vector is definitely pointing in the positive z direction. Okay, so that's why I can rewrite it that way. Again, we're just trying to get this expression in a form that is familiar to you. I also, if I wanted to, I could take the dot product of p and the r vector, okay? That is going to just be equal to what I just said p is, which was q d z hat dotted with the r vector, okay? If I look at that, okay, so the r vector dotted with the z hat vector, that's just going to result in multiplying the z hat vector by the z component of the r vector, which is the same thing as z. Okay, so that's going to give me q d r z, which is equal to q d z. Okay. That just basically tells me that q d z is the same thing as taking the dot product of our dipole moment p and our r vector. Okay, again, because we're just going to get the magnitude of the r vector that happens to be in the z direction, okay, which is going to be z. I could draw that over here. This is p. And this is our r vector. Then this is going to be our rz vector, which is just equal to z. Okay, so the whole point of that is I'm going to rewrite this formula one more time. Okay, so we're going to get that the potential of a dipole is going to be equal to 1 over 4 pi epsilon naught. Okay. Times p dotted with r over r to the third. Okay, that's what I just wrote down. I can also write this another way as 1 over 4 pi epsilon naught times p dotted with the r hat vector over r to the third. I did that. I made that, sorry, that's r squared. And I can make that substitution because I can sub in that r hat is equal to the vector r divided by its magnitude. Okay, so that gives us one more way to write our potential of a dipole consisting of two different charges. Okay, but this is a little bit of a special case. I just want to remind you guys, right? This is what we'd say a dipole consisting of two charges, and this is when r is much, much greater than d, okay? So it's important to know that this is an approximation far from the charges. Okay, some things to note. It is distinct from Coulomb's potential okay, and it's distinct because it falls off like 1 over r squared, okay, so that's more rapid. And it's also not symmetric, okay? So if you remember Coulomb's law, right, is symmetric, spherically symmetric. So you could rotate that charge however you wanted. It wouldn't change the potential around it, okay? The dot product gives us different results for different orientations of P, which is a vector, remember, that points in the same direction of D, and R, which is a position vector from the origin to where you're trying to evaluate the potential.